Hello and welcome to CCSF's Astronomy 17 Makeup Lecture. Uh, if you're one of my students, you'll recognize my voice, and so you'll know you're in the right place. If you just blundered into this YouTube video looking for something interesting about Venus, this is a class where I'm going to be referencing a textbook and sometimes some previous lectures that were given in person. But all of this should stand on its own, so I hope you'll find it informative if you do stay with us. And the topic of the day is Venus, Earth's twin sister planet. And why do we call it Earth's twin sister planet? Well, because so many properties of this planet are very similar, if not nearly identical, to Earth. Size. It has a diameter of something around 90% Earth's diameter. That's only slightly smaller. Mass. Again, only a small fraction smaller. Overall composition. We can make a good guess at that by taking the mass divided by the volume. You get the density that way. The result is pretty much the same as Earth, so we figure it's the same proportions of rock and metal. Distance from the Sun. Also, this is the most similar planet in the solar system to Earth that way. Its distance from the Sun is 0.72 AU, 72% of the distance of Earth from the Sun, but that still means that it swings only a fraction of AU away from Earth when both planets are passing each other, and that means that Venus gets a lot closer to us than Mars ever does. It is the closest planet to us in so many ways. So the image I've got on the screen here is not a very good one. It is a bit contrast enhanced to try to bring out just a few details in the clouds, but really this is what you see of Venus when you look at it. It's cloud covered, it's essentially featureless, and the surface is totally left to your imagination. Back in the 1950s there were a lot of rather bad B-grade science fiction movies that were all set on Venus because the imagination was given completely free rein to imagine what the surface was like under those clouds. They all imagined a place that was habitable in some way. Warm, cool, tropical, rainy. None of them had any idea that the conditions were going to be like what we were going to discover in the next decades. A surface temperature of 900 Fahrenheit, hot enough to melt lead, an atmospheric pressure strong enough to crush the hull of a submarine. A very, very, very hellish place. But we'll discuss the surface in just a moment in this lecture. Let's start by just taking a look at the clouds. This is a visible light picture. Contrast enhanced so you can at least see a few details, but in visible light you don't really see much. So let's switch to a different picture, this one in the ultraviolet. It shows the wind direction, some circulation, which way the clouds are swirling around, in much more clear detail than the previous picture we started with. The previous picture was closer to what you'd see with your own eyes in visible light, but was still very much contrast enhanced. In ordinary direct view, if you flew up to Venus and just looked down, featureless, white. You can't really see a thing, no details at all. But this picture of the ultraviolet light reflected by Venus manages to show where the wind speeds on the planet are fastest. The boundary between the top of the troposphere and the bottom of the stratosphere, where the winds actually circulate around the planet as fast as one loop all the way around Venus in 4 days. Winds deeper down towards the surface we've been able to measure are much, much slower. The fastest wind speed we've ever managed to record by a lander at the surface was 6 kilometers an hour, which you would barely feel. The atmosphere circulation in general is just running from the equator to the pole very, very slowly. The equator is hardly any warmer than the pole because the atmosphere of Venus turns out to be extremely dense. 90 times the atmospheric pressure at Earth's surface, and that does a very good job of spreading the heat around. But this slow movement of air from the equator to the pole sets up just one single cell of circulation in each hemisphere. Contrast that to the 3 cells we described on Earth, from the tropics, the temperate zones, and the polar regions. Earth rotates so quickly that the Coriolis effect was dividing the circulation into those 3 cells. Venus, on the other hand, is the slowest rotating planet in the entire solar system, taking 243 Earth days to spin once. That barely affects the air circulation on Venus at all. The only reason the wind speed seems to be faster at the top of the troposphere and the bottom of the stratosphere is that absorption of ultraviolet light from the sun is inputting just enough energy there to drive some wind where the atmosphere is thin enough to pick up a bit of speed. All that thick cloud cover actually reflects the majority of the sunlight that reaches Venus back into space. So one other way in which Venus was expected to be very, very similar to Earth was in how much sunlight actually reaches the ground to heat up the ground surface. We could see with our telescopes for centuries, all the way from the 1600s on to the 1950s, that Venus was all covered with cloud and very reflective. So it was easy to imagine that the amount of heating on the ground surface was very similar to Earth, perhaps colder, perhaps warmer, just a little, but certainly not that much different. The actual fraction of sunlight reflected by the clouds of Venus is more than 60%. Some references give that number as high as 75%, but it depends a bit on what range of light wavelengths they are comparing. Recall for Earth that the fraction was only 39%. When we are trying to consider how warm Earth's surface is, we have to consider that 39% of all the light we receive from the sun, which would heat the ground, is actually reflected back into space by the surface, by the clouds. In the case of Venus, it is a much bigger fraction. So, this is why astronomers used to think that the surface temperature would be comfortable, maybe even cold. I mentioned all these 1950s B-grade science fiction movies that were set on Venus. Some of them made it a tropical, sort of steamy place. Some of them made it a cold place. Some of them made it room temperature. But they all figured that it wasn't going to be that different from the surface of the Earth. Indeed, even if you took away the clouds and let all the sunlight into this planet that is a fair fraction closer to the sun than Earth is, the expected temperature of Venus without clouds still was only 30 degrees hotter than on Earth. Well, that doesn't jive with what I said at the very beginning of this talk, that we now know the surface temperature is 900 Fahrenheit. Something must be going on to raise the temperature to the So this is a temperature profile graph for Venus. The red line in the graph is telling you what the temperature is for any given height in the atmosphere of the planet. It reads about 750 Kelvin down at the surface. It reads about 400 Kelvin at the bottom of the clouds. Remember, earthly room temperature is a little less than 300 Kelvin, so you can see that the cloud tops would actually be cold by earthly standards. 750 Kelvin is the 900 Fahrenheit that I've mentioned earlier, is hot enough to melt lead. And from the clouds down to the surface, through the layer that we call the troposphere, everything is in hydrostatic equilibrium, where temperature and pressure get less and less with increasing height because there is less air above providing pressure. Then the top of the clouds would be the very bottommost part of what passes for a stratosphere on Venus. And troposphere and stratosphere are the only two layers that really deserve any sort of mention here. Troposphere, as on Earth, is where all the weather takes place. The clouds are technically part of the troposphere, and the stratosphere is above that. Now, the chemical symbol for sulfuric acid is what is written there, H2SO4. There is also some sulfur. Ignore the question mark. I'm using an old graph. We know there is sulfur there. And the atmosphere in the troposphere is labeled as CO2. The clouds are not CO2. The air underneath the clouds is CO2. It would be pure, clear, no clouds at all for the bottommost 40 kilometers. Those are very high clouds. The sulfuric acid is a complicated molecule, H2SO4, and it would be broken apart by ultraviolet light. That there persist sulfuric acid clouds tells us that it must be being replenished somehow by volcanic activity from below. I've mentioned already that most of the gases that come out of volcanoes are water, carbon dioxide, and nitrogen, but sulfur compounds they come out plentifully enough, as anyone who's visited a volcano and smelled it knows. And we figure that that must be where all the clouds of Venus are being sustained. So you could conclude that you had a volcanically active planet even before exploring the surface. But trying to get down to the surface under those conditions, not easy. So here's a picture of one of those Soviet spacecraft, though not one of the first ones. I mentioned back when we were covering Chapter 7 that there was something of a gentleman's agreement between the two superpowers of the late 20th century, the Soviet Union and the United States of America, and that while both of them raced to reach the moon and land a human being on it, the rest of the solar system was going to be divided. The Soviets were going to go over towards Venus. The Americans were set to explore Mars. And little did the Soviet Union know just how much harder their task was going to be. Nevertheless, they beat us to landing a spacecraft on another planet. December 15th, 1970, the landing of Venera 7 is the very first time humanity ever landed a craft on another planet in the solar system. Sure, we'd already had human beings walking on the moon in 1969. But to land on another planet, that was big press. And given that this was a planet with a surface temperature hot enough to melt lead and enough pressure to crush a military submarine, my hats are still off to the Soviets for pulling this one off. The very first spacecraft that they sent to Venus didn't even make it to the surface. Their hulls were not designed to withstand 90 Earth atmospheres of pressure. Their hulls were crushed. Finally, the Soviets started building them much hardier, like tanks. Venera 7 was the first to make it. Venera 9 was the first to actually take pictures. Neither of those are what's shown here. I think this is Venera 13 or 14, but maybe even a later number. They continued on into the 1980s. I just like this particular picture because it shows the reddish color of the landscape because of the sunlight filtering through those thick sulfuric acid clouds. We can use the picture of the part of the spacecraft in this picture to calibrate real color and know that the rocks would actually be a very boring slate gray. But that's not slate, that's basalt. Every single one of the Soviet spacecraft that managed to land anywhere on the ground and survive long enough to take some samples, just for a little bit of analysis, we're pretty sure that they all landed, every last one of them, on basalt. So the surface of Venus must be primarily basalt. Well, that's also true of Earth when you think about it. We've already learned that the ocean floor crust of the Earth is basalt, and that's about 3/4 of Earth's surface. So there may be some parts of the surface of Venus that are not basalt, but this is definite confirmation that Venus is a very volcanically active world, that the majority of its rock comes from large runny lava flows.